start with a bit of prehistory. So my field is nonlinear science, and many people really from this area went to biology nowadays. And the attitude, though, is quite different, because in nonlinear physics, what we're trying to do is to have a generic scenario. And one can get really quite a complicated behavior in simple systems. In biology, it is quite different, because people are interested, after all, in specific things. And we have to work on a very precise level if the medical doctors would be interested in the results. But there are still common features. Then again, what I have to say that in nonlinear science, actually, there were also particular applications, but these applications were mostly connected to reaction diffusion equations and to fluids. And what was missing is elasticity. And it was missing really for a reason, because in solids there is no motion, and if there are some pattern formation phenomena in solids, they are mostly connected to crystalline structure. But in biology and in new biomimetic material, what is relevant is soft matter. And in soft matter, the deformations are very much connected to other phenomena. And so this is what I will be mostly talking about, how the coupling, how the patterns which are formed by coupling of deformation, polarization, and chemical transformation. And here you see the scope of the model. I'll talk about mechanical instabilities in active layers, and this application to the spreading of tissue. And my last work, my current work, is not on biological but on biomimetic materials, where we have much more information and we have much better control of the systems. So here is the basic scheme, which can be varied in different applications. So we have basically three factors. One is positions and shape, though this is a deformation field, concentration or chemical signals, different chemical signals, and polarization. And this is how this loop can operate. Say, deformation induces chemical signal induces polarization, polarization induces active forces that deform the system. This is one basic scheme, and which of course can be modified in many various ways in particular systems. And in biology, this part is extremely complicated. And in our models, we usually have only simple parts of this. But these things are quite universal: polarization and deformation, and coupling can be in different way. Well, polarization. What is polarization? Biologists actually define polarization in many different ways. So anything actually which deforms, which makes the medium, the cell or the tissue anisotropic, is called polarization. It can be shape of the cell, it can be anything. And it has, in physics, of course, it has much more specific value. And there are many examples. Here is just a few. This is one. In spreading tissues, there is a certain protein kinase which is necessary for this. And in cytoskeleton, myosin is the actor which induces deformation, and also its absorption is depending on compression. And there are many examples when a change of protein conformation induces some chemical reactions, produce some enzymes. Composition affects polarization, and this is, of course, all motion is triggered by some chemical signals which polarize the tissue or parts of the skeleton. And this we'll also see in biomimetic materials, about which I will talk a bit later. Polarization induces deformation. And these actin stress fibers, they say they have pneumatic polarization in standing cells, and they have vector polarization in moving cells, and this polarization of the stress fibers is very important, of course, in all motion and in reshaping of cells. And then anisotropic deformation of biomimetic materials, about which I will talk. So this is the basic mathematical approach to this. So we consider these systems as weakly departing from equilibrium. Well, they're not really weakly departing from equilibrium, but the mechanical and polarization part can be considered as such. And anyway, it brings some order into the system. And so we define free energy. And the free energy can be divided in three parts. One is mechanical elasticity, another one is pneumatic, and the third related, which may be or may be not present, which is related to chemical compositions. And this will be an integral which is depends on three kinds of variables. Deformation, polarization, and composition. And the dynamics is a kind of overdamped dynamics. In biological and biomimetic systems, we actually can forget Newton's law. Inertia never plays the role, and the dynamics is a kind of Aristotelian dynamics, which moves towards the equilibrium. So each variable evolves according to the variation of the free energy with respect to this variable with some friction coefficient. And to this, we can add non-equilibrium terms, active forces and active, which we can do really anything here. There is a lot of freedom, too much freedom maybe. Now, we usually deal with thin layers, like an epithelium layer of cells, and also sheets of biomimetic materials. And this can have variable thickness. It may be constrained by volume concentration, which is not necessary actually because of the osmotic flow. And the deformations in soft matter are large. typically large. And so the classical linear mechanics is not very well applicable here. And what we do, basically, we have some reference state. We can choose. This reference state has no stress. And mechanical stress is induced by any deformation of this stress. So we define deformation as a derivative of a position with respect to the reference position in the reference state. And this is not symmetric, and it can be symmetrized in this way. And the extension, which is in linear mechanics, it is just the trace of this tensor is basically should be the determinant. Now the overdamped dynamics is defined like this in the usual way, and here we define the stress as a variation of the energy with respect to deformation. And to this, active forces are added. Now polarization. Polarization is here in such kind of a theory. It should be a correct definition of polarization. It is not really related to its origin, but what is important here is the vector character of this polarization. So here it is, and we construct the energy functional, which is Landau-Desjardins functional, by collecting lowest order terms which are compatible with the symmetry. And here it is for a vector polarization. So we see this, so here what is present here are all scalars that we can construct using the polarization and its derivative with the total power not larger than 4. And this is all that we can construct. And then there is another term. If there is here a variation of concentration, then we can add another term, which makes, this is what will make the dynamics interesting. And so here, if we have just here, it is of course just this. It is irrelevant. But if the coefficient here is variable depending on concentration, then variation of this energy is non-trivial and gives such kind of term, depending on concentration. So when we do variation, this is what we obtain. This is the such usual terms, and here the red is the added term which gives the influence of concentration. Now, what stands in here is moving rotational derivative, which physically means that if the medium is deformed and there is a polarization there, the polarization vector moves with this element and rotates. And when we compute, we don't really use analytical expression of this derivative, which is written here with velocities, but all computations that I will show they're in Lagrangian frame. So we have a certain, we start with a certain grid, and each point of the is moved, and followed, its motion is followed, and whatever concentration and polarization sits on this grid moves with it and behaves in a proper way.
What is a x squared?
X.
So kappa is the curvature of your
This is so this integrates over all region in the reference frame.
But what is ax squared? What is ax squared? In the denominator.
The denominator where?
There.
Here, okay, all these are coefficients, really. This is, what is it? This is, I really don't forgot where it comes from. It is here. This is the height.
That's the height of
this is the thickness, and
but yeah.
You can forget really. You can forget this. It is just coefficient for scaling.
And how can you have in the free energy this red term that is dependent only on the first derivative of p?
This one.
Yes. Shouldn't the energy always have something which is independent on the sign of your gradient? So if the gradient is increasing or decreasing, you should still have the same energy contribution. Should it be this? Usually we see energy function as something like that squared.
Yes, usually
yes, the E is squared.
Yes,
but
exactly.
this is important because really in this term it will be not. There will be a substantial difference between extension and compression.
So it depends on sign.
On time.
On sign.
On the sign of the gradient.
Yes. It depends on sign. Actually, here there should be a coefficient depending on sign here, and they will appear like somehow it's missing in this form. It has to depend. It has to depend on sign. Well, the concentration why it is here because of the sign, because the concentration here. What we use is not concentration by itself, but deviation of concentration. Which can have different signs. So when you see later, say, negative concentration, you don't be astonished. And now here is a basic model. So this is the equation for a chemical signal, which depends here on the side on the extension with some coefficient. So this is added here. This additive term, which means that deformation induces formation of chemical signals. Now, this is the term from polarization, which means that the gradient induces concentration gradient induces polarization. And here is the active force, which is defined as something proportional to polarization. So this is how this basic scheme is realized. Now, what you see in this slide is the linear stability analysis of this system. So you have here. You have here, it's in general formulation, there are 5 variables. two components of deformation, two components of polarization, and one concentration. In the linearized equations, they're reduced to three. Besides concentration, it is strain and splay. And here is quite easy stability analysis, which shows that there is here a stationary instability and an oscillatory instability. Here is they are plotted as a function of this parameter, and there is a gap between them.
So this is really, it's interesting that this is reaction diffusion with cross diffusion, in fact.
Well, it is not reaction. It is not reaction diffusion.
I mean, yes, but
This is the reaction diffusion part. Well, you can say that they really have the same structure.
they have the same structure. Yes,
The same structure, but only in linear. But only linearly they have such a structure. Because in reaction diffusion equations, there is an algebraic nonlinear part. And here, nonlinearities in this system, nonlinearities are also in differential terms.
Yes.
But
yes,
when
yes,
you
yes.
reduce it to this, you have, but reaction diffusion equation does not play reaction diffusion equation because you see there is such a part. So the general reaction diffusion will be with the diffusion matrix. And so here is the diffusion matrix, you can say, which is not diagonal.
Yes, yeah, that's.
And here we can have, well, this is the oscillatory instability. Here is just two phases of this oscillatory instability. Well, it behaves in such a way because oscillatory instability is here on a finite wave now. Now, what is this? And stationary stability is on a zero wavelength, so it does not lead to a pattern, but it leads to a ripening or coarsening process, so that characteristic length changes with time. As you see you see here how this structure evolves, and here is one section of this structure. We have concentration minima, and in this concentration minima, there is also compression, and the polarization direction changes abruptly here. So you see polarization is directed in this way, so here is motion directed. And here you can also see this. Somehow it goes too slowly. And this goes so eventually there will be only two domains. But this is interesting when it is in spherical geometry. In spherical geometry, what you would have, it will lead to permanent polarization. Permanent polarization and permanent concentration gradient. because the sphere, topologically, two defects must survive on two poles on a sphere, and the concentration arranges accordingly. Now, this is application of this to epithelial spreading, and here, see, this is some model wound, which so wounding can be with injury, and this injury sends a chemical signal, which and this chemical signal excites the kinase, and this causes the spreading. But we can do is more gently by just letting making a peel off just to make a free space for spreading, and then it also spreads without a signal. So signal, but signal is necessary, because if it is suppressed by a drug, then there is no spreading. So these are two sets experiment. This is earlier experiment where chemistry was followed, and in these experiments mechanics is followed. And this is a characteristic really for biological research. We never have really enough data for modeling. So what we see here is that spreading does go if there is free space, and there is a chemical which is necessary for this. And so we built up model which is similar to the model, this feedback loop is similar, but it is done more practically, so we have to suppress here nonlinear development of instability. Also in this system, instability actually is not linear but quadratic. And what the only thing that we can do is to have some basic similarity to the experiment. Qualitative similarity. This is how we model the boundaries. This is important here because so here it is similar to wetting. So there is a wetting force on this boundary. There is just free boundaries. There is no chemical flux and branching directional derivative of polarization, but this is important condition for force. So there is a spreading force for call it a wetting force at the boundary, and this is in this actual computation. It is small, but it is necessary to trigger the motion, and this is how it goes. In the end, we don't have anything like it, because this is a quadratic instability, and but gradually polarization develops there. Here it extends. The extension causes the signal to be created, and the signal enhances expression, and it is very unstable. And in all experimental picture that I showed before, you also see this instability, transverse instability. And here is experimental pictures of polarization, which are different in the bulk. there is almost no polarization in the bulk, but there is strong polarization in these fingers, which develop on the surface. And here we imitated this in the same way in the computation. And, but it is interesting really how it is defined, polarization. So polarization experimentally is defined by position of organizing the center of microtubules in the cell with respect to the nucleus of the cell. And we define it in a normal way, as it is defined polarization in the Landau-Desgen function. And the picture, in picture appears to be similar. There is also very little polarization in the bulk and strong polarization in the finger. Now I go further, and from the vector polarization we pass to pneumatic polarization. Pneumatic polarization is characterized, it has no direction. It is not a vector but a director, which has only orientation, but is symmetric to reflection. And I will mostly talk here. So we had really some papers, a paper on biological application with this information. But I will talk about these pneumatic elastomers. Pneumatic elastomers is basically the pneumatic liquid crystal which is polymerized, and so that these mesogen units which constitute the pneumatic liquid are attached to polymer chains. And this causes such an effect that if we go from isotropic unordered orientation to ordered orientation of pneumatic units, then the polymer chain extends. And this polymer, this material is a soft material. The elastic modulus can be regulated by a degree of cross-linking of these polymer chains. And this offers really a lot of applications, about which I will talk very briefly, and it is now a very lively, very active area of research. So, when we consider it, the basic scheme, this slide is actually identical to what I've showed before. There is elasticity, elastic energy, and pneumatic energy, and some composition energy, and all of them dynamics. What is different? The pneumatic energy, because there is a different tensor character of the other parameter field here. So it is, so we consider two-dimensional. Geometry will be a sheet similar to epithelial layer we were talking about before, and the pneumatic orientation changes only in 2 dimensions, because it is described by, it has to be described by a tensor. And this is a 2-dimensional tensor. It can be written in such form with 2 variables. It can be written in this way. This is the order parameter, scalar order parameter, and theta is the orientation angle. And this is, again, the Landau-Desgen pneumatic energy density. It is not the most general equation, actually. The most general equation would have here some 6 elastic coefficients and more terms. Here it is elasticity is pneumatic elasticity is independent on orientation. In this case, we can construct only these terms. But it is actually more general than what you see in Dejean's book, Dejean and Pro, because here it is very important for us that also the scalar of the parameter should change, because we are interested in spontaneous formation of polarization. And here the deformation is the treatment of deformation here is different because there is here not only elastic deformation but intrinsic deformation. And the mechanism for this was developed in plant growth. So you start with a reference configuration, and then there is a virtual configuration which is grown but stress-free. And then here is the actual configuration. This is drawn in such a fancy way in this paper just because it is a virtual but not a real configuration.
But your final configuration is
so the final configuration. So now here is a deformation tensor, and the deformation tensor here has to be split into elastic deformation tensor and intrinsic deformation, which in plant growth it was called the growth factor. I prefer to call it intrinsic deformation. It is different because in plant growth it is an isotropic growth. So this would be a diagonal matrix. Here, this matrix should depend on this tensor intrinsic deformation should be related to deformation to the pneumatic tensor. And this is the simplest relation that we can construct. This is the extension factor. And this factor makes it area conserving. And so, what remains? So this is the observed deformation, but elasticity depends only. The elastic energy depends only on elastic part of deformation. And so elastic, this elastic deformation here, it can be diagonalized, and only this has to enter the elastic energy. And so the elastic energy, you see it, you see it here. It was without intrinsic deformation, it would be just a deformation tensor. But with this, we have to express the deformation, the elastic part through observed deformation. And this would involve dependence on the pneumatic order parameter. And the expression, actually, this expression is would be very complex. It would involve also higher order terms, but in the beginning we used this complex equation, but then we observed that we shouldn't really involve terms of higher order in the pneumatic order parameter than it is in the Landau-Lejeune function. And so then we started to use such an approximate equation which does not include higher order. And so this gives such an elastic energy. And this is what is important here, that the elastic energy depends on the order parameter. And when we obtain the deformation dynamics, it would depend the dependence on the derivative of the order parameter. Now, in liquid crystals, in usual liquid crystals, there was also dependence on the stress, on the liquid stress, and this is the Ericsson stress. But you see that here it is of higher order. It is quadratic in the pneumatic order parameter, but here it is much stronger with linear dependence. So this in solids, this can be neglected. We really included it in computation at some stage, and then so it has no effect at all. And now pneumatic dynamics. When we compute pneumatic dynamics, we also have to obtain a term which comes from the term that comes from the elastic energy. And so it comes here, and so it includes elasticity. The correlational derivative also has here more complex form. And this is in this system we obtain also static and oscillatory instabilities, and the static instability induces first when we start by quenching the isotropic state in the condition when it becomes pneumatic, there is a lot of defect forms, and then they gradually disappear. And normally, without effect of elasticity, they would disappear completely, because this computation, it is as usually you have it with a periodic boundary condition, so which is topologically on the terms, but in the computations they remain. Well, I have a movie, but I have no time really for this, because I have still more material, and the defects remain. And why they remain? Because it is, after all, it is at this stage is undeformable. So you cannot extend all deformations are in 2D, but the size of the stores is fixed. And so the system cannot really, if it gets rid of all defects, then there will be a strong mechanical stress. And so defects, some defects remain. And we later, this is still unpublished, we explored it more. This is such a system. This is a cylinder with clamped boundary. So in this system, we impose on the boundary, we impose orientation, either parallel or normal to the boundary, and we can obtain here one-dimensional solutions. Here is the equations. It is possible to obtain here such a solution. We are also only the order parameter and the orientation and circumferential deformation change. But no defects form. And this will be described by this one-dimensional set of equations. And the structure that we would obtain, it is such kind of a structure. So you see here the orientation, it changes like this, and the system expands it deforms circumferentially. But in other computations, we would have still defects. So this solution already is not one-dimensional. So all of this gives really a balance. It all depends on the balance between elastic, between pneumatic elasticity and mechanical elasticity. And here is what you see here is the bifurcation diagram. It depends on rescaled length, which is also at elasticity, and so we can obtain here. This is the solution containing defects, and this is a solution which does not contain defects, and their energy interchange. And this is a solution. The solution, of course, when it has defects, it should be a minimum 2 defects by topology. This is a solution with 4 defects, which has a higher energy, but it in some computations it will also appear, and it depends on basically on the random initial conditions. So this would be.
Do you know about stability of these solutions?
These solutions are stable, but some of them are the lowest energy solution is absolutely stable, and the other solutions are metastable. Here is the example of evolution. Here is you see pair defects, and there is another pair defects which is on the boundaries. And it's this computation goes on. Here is a speed up, and nothing changes. Here it shows the deformation, and the deformation is both in y and in circumferential, and also a bit in the direction between the clamped boundaries. Now this can be developed more, and concentration is added. And this is experimentally realizable because there is such a messenger which can be by ultraviolet light. It can reorganize into non-messenger. So that here the pneumatic isotropic condition depends on this concentration. And here comes this is still equilibrium system, but we are allowed to bring into the pneumatic energy also such a differential term which couples the gradients of concentration and order parameter. And this is the most interesting term here. This is how the dynamics goes. Here, pneumatic dynamics here depends both on deformation and on concentration. And the signal of concentration dynamics depends on the order parameter. So we are returning basically to this scheme which I had before, but it operates even near equilibrium. And so here is how the dynamics goes. You see here there is a biphasic region, and here two phases with low and high concentration. So here it is pneumatic region, and here it is almost isotropic region. But you see here a certain orientation of this pattern, and this orientation is not random, and we see it when we start not from isotropic state, but from perfectly organized pneumatic state. And depending on these coefficients, the concentration in homogeneity organizes either this way, normal to the pneumatic direction, or parallel to the pneumatic direction. With zero, it will be violent. And this can be seen even in the linear analysis, which is quite difficult to read here.
Are these independent of the initial conditions? The
And
initial configuration?
this does not depend on initial condition. In this case, so such details of the pattern may depend on the initial condition, but the orientation does not depend on the initial condition. And so this is it is a phenomenon of anchoring of the orientation to the boundary between isotropic and pneumatic state. So well, I have really a short time left, but there is, there is now. I'll go from 2 to 3 dimensions, because this, if you allow these sheets to deform, then you can obtain different kind of structures. This is an experimental picture. See, here is they can induce, impress into the sheet a certain orientation. And here, they impress. This is charge 1 defect in each square. And so they start with a flat sheet, and after, and you remember there was one. No, it wasn't yet. So this deforms in such a kind of a structure. So after it goes from pneumatic state by heating to isotropic state, we obtain such kind of a structure. And this now, this is another example when you, by light beam, bends the pneumatic sheet, and this actually was used for this sheet was made to swing. This example, it is not a pneumatic. This is swelling gels, which also can have different structures. And now, what we have to do with this is that the change from pneumatic to isotropic state, or other way around, brings about a metric transformation, so that the interval which we had in one state is transformed in this way. And we can, in this way, we can construct a new metric. And by this metric, we can restore the shape. And these are the simplest example which we have, if we have such a structure. So then it compresses in circumferential direction and extends in radial direction. The result is a conical structure, and this is what you've just seen in the experimental picture. It is much more complicated when there is such a state, when it compresses in direction and extends in circumferential direction. Then each circle is deformed in such a way, and it is already quite a complicated structure, which I will not talk now. Now, the unit charge defects are really not typical for this system, because the lowest energy have defects of half-charge defects. In vector polarization, unit charge defect is a basic structure, but here it is half-charged, so because rotation is only by 180 degrees by pi in pneumatics. And so here, this is, if we take a vicinity of half-charge defect, this will be the order parameter. This is the metric that we can constrain. With metric, we can obtain the Gaussian curvature. But we cannot obtain the actual shape analytically in this way. To obtain the actual shape, and there is no symmetry here. And so to obtain the actual shape, we need a numerical computation. And here it is. So here is the director field. This is +1, and this is +1/2, and this is -1/2. And they have completely different structure. You see that this one has such a pi symmetry, and this has a triple symmetry. This is a Gaussian curvature, and this is the deformed shape, which is computed numerically. And they liked really these graphics, and so they put it on the title page of the last issue of PDE. Here are more forms. Here is how, for an ellipse, we can obtain analytically the structure. And because in an ellipse there will be half-charge defects in foci of in the elliptic coordinate system, so we can obtain structure analytically, and this is how it is reshaped, and it is different with different orientation with respect to the boundary. Here it extends in this way, and here it extends in this way. But the shape is very complicated, and this shape actually depends on the parameters of the models of the model on bending rigidity. This we can also obtain shapes with structures with -1/2 defects. This is the structure here. In this case, the structure was obtained numerically too. There is no, of course, analytical, and it depends. The structure depends on how we make up this whole. You see here defects like this. Here defects like this. And here this is identical, but the location of defects is different. It's also deformation. But then what we can do with it? We can also make deformation dynamic. And here you see this is a simple example. This is a wall, just a line. And it extends, and there is a light beam or maybe chemical reaction which causes isotropic pneumatic transition, which causes extension. It is also important that the friction should be different in say this is a red pneumatic part and this is an isotropic part. In the limit of when this part does not move and this moves easily. We can obtain radial very easily how that it should move, because it extends under the beam. When it comes from here, it extends, and then as the beam moves, the extension propagates, and as a result, there will be such a speed of motion, depending on the velocity of the beam and on the length of the beam. This is how it goes. So here I see in not such a with different velocities, with different friction coefficients, but not 0, 1. This similar thing really how it moves when it is a cylinder. The beam goes here other way around from right to the left, and you see with each beam passage it moves in a fixed distance. Now with this structure, this experimental structure that we have shown before, so here there is a chain of we had here a pneumatic, we have here a pneumatic with a defect, and it changes, and it has such a conical structure, like in this picture, and here what is going on when it starts to, when the beam goes. You see it moved, and then it will move direction. So it is like a peristaltic worm, basically, all this, but here is it is a more complex shape here.
Can it get stuck? So because it seems like it jumps and it has to
Here,
so that it doesn't jump to the next one but stops in this
yes,
process.
because the rule, it needs friction, otherwise it will not move. So here in this model, it is assumed that when it's the point that stands on Earth cannot move. So it can move only by lifting, and so it is not really a peristaltic worm, but it rather the worm was before. But this system is. Moves, really walks on these legs. It is really, this is how the ellipse, if we start with this elliptic structure, here the points is where it touches the Earth and does not move, and so here is pneumatic state, here is isotropic state. But the ellipse is very disordered, and it almost does not move. It actually wobbles rather than moves. And we have now really, we're preparing really some several animals to publish. And also such animals can also swim. So
really you're continuously pumping energy into the system from that
yes,
side,
yes, we're pumping the energy by light or by chemical reaction, which changes all the time. So this is a summary. There is we started with a simple feedback mechanism, and which gives coursing and permanent polarity. And then a bit different model was used to obtain, to model spreading, which has a lot of instabilities. And the last part was about deformation and ordering in pneumatic elastomers. First, just by deformation and interaction between deformation and polarization, and then also with concentration feedback. And the last part was about three-dimensional deformations. And here my young co-authors, Mikhail Kerb and Andrei Zakharov. This is a typical Israeli landscape. This is a typical Russian landscape. And thank you.
A few questions, just past the hour. Out of curiosity, what numerical method did you use to solve these
Well, this is a finite element.
finite elements?
Finite elements and this Lagrangian dynamics. Well, it didn't have really, the finite elements is mostly in this last part, three-dimensional information. So, what is in two-dimensional was just Lagrangian dynamics with points moving according to the laws of motion, which I have shown here.
If no further questions, let's